In this topic, we are going to cover Pycryptodome. Pycryptodome is a fork of the Pycrypto library that has been enhanced to add more functionality and also security fixes to that original Pycrypto library. The last commit that was made to the official Pycrypto library was back in 2014. So in this lesson, we will be using Pycryptodome and not the older, less secure Pycrypto library. This lesson won't go into detail on cryptography or make recommendations on when to use different types of ciphers. We will instead just use Pycryptodome to perform common encryption tasks. And Pycryptodome can be used for symmetric ciphers, asymmetric ciphers, hashes, message authentication codes, and more. To use the library, let's start by installing it with pip. Pip install Pycryptodome. And now that it's installed, we can start using it. Let's start with using AES, a symmetric cipher. One of the first steps when using a symmetric cipher is to generate or use a sufficiently random key. Pycryptodome supplies a function, crypto.random.getRandomBytes, that returns a random byte string of a length that we specify. So let's create our key from crypto.random import getRandomBytes. We can create a key of length 32 and we can print this out. Crypto demo.py, execute this. And we can see that with each execution, we get a different key, which is made up of different random bytes. And the length of the key that we need will depend on the type of cipher that we are using. So this key is 32 bytes or 256 bits in length. We can verify this. And for a symmetric cipher, the key we will use to decrypt will also have to be the same key we encrypt with. So take care not to lose this key when you're performing encryption. And as we can see, this key is very random. And every time we run this script, this key is very likely to change. So if you don't want to use and remember a completely random key like this, you can also use password-based key derivation function. The idea being, you can use this function to generate a byte sequence based on a string provided from the user. And Pycryptodome supports this. So we could say from crypto.protocol.kdf import pbkdf2. And when using pbkdf2, we also need a salt. And the salt is used to help prevent against dictionary-based attacks. The value doesn't necessarily need to be kept secret, but it should be random for each derivation. So let's create our salt using getRandomBytes again. We can also specify our password, hunter2. And this is the secret password which we will use to generate our key. Then we can generate our key. We pass in the password, the salt, and the dklen, which is the cumulative length of the keys to produce. And now we can print this key out, and the length of the key as well. And we can see different outputs here due to the different random salt which we are using each time we execute this function. However, if we use a static salt, such as this value, and execute this, we can see that by using this key derivation function, our output key is consistently the same, due to the fact that our password and salt are also the same. And so that means that we don't necessarily need to store this whole key now, as this key can instead just be generated every time that we want to use it, as long as the user provides the same password. So if we'd use a different password here, we can see that the generated key is also completely different. And so now that we have a key, we can start to actually perform some encryption. So let's import the AES cipher. And let's also import a padding function. Because for a symmetric cipher, we also need to be able to pad our data up to the length of a block size. And again, this is already implemented within Pycryptodome. So let's encrypt the string. Encrypt me. And now we need to create our cipher. So we can use aes.new. We specify our key, and we also specify the mode. So we'll be using CBC mode here, which stands for cipher block chaining. And now that we have our cipher, we also now have our initialization vector, and we can actually encrypt data. So we could print out our IV, and we can encrypt our data. By first padding it with the block size. And then we can print out our encrypted data. Fix our typo here. And here we can see our initialization vector and our encrypted data. And so there you have it, data encrypted in AES using Python. And now that we have encrypted the data, we can also decrypt it as well. However, when performing decryption, we need to be aware that a cipher object is stateful. So that means once we've already encrypted a message, we can't also perform decryption with that same object. And this goes both ways. So that means to perform our decryption, we need to set up a new cipher with the same key and also in CBC mode. Then we can perform the decryption. Of the encrypted data, and we can print out that plain text. We can execute this. However, we can see here that we still have jumbled data. We don't see this encrypt me string anymore. And that's because we're using another random IV. So we instead need to specify our IV here. We can execute this. And here we can see, as expected, our plain text output, encrypt me, and we also have 5 bytes of padding. And so to also remove this padding, we can import unpad, and now we can also unpad our decrypted data, specifying again the block size. And we can execute this again. And we can see that we now have our original plain text, encrypt me, with the padding removed. As well as symmetric block ciphers, we can also use symmetric stream ciphers. And as already mentioned at the start of this lesson, this isn't an example of using these ciphers securely, but we can still perform similar encryption and decryption using Arc4 with Pycryptodome. So let's first import it from crypto.cipher, import Arc4. Now we can create a new cipher. We can use the same key. We can encrypt our data. We can print it out. We can execute this. And here we can see our encrypted data, which hasn't been padded to a block size. And now we can also decrypt it. So we need to create a new cipher. And now we can obtain the plain text of the encrypted data. And we can print this out again. And here we can see we receive the plain text encrypt me as expected. And if you want to encrypt data with an asymmetric cipher, such as RSA, then you will need to either have access to a public and private RSA key pair, depending on what it is you're trying to do, or you can use Pycryptodome to generate your own. So let's do that. Let's import RSA. And now that it's imported, we can generate an RSA key of 1024 bits. And now we can password protect our key with our password of Hunter2. And we can print this out. And here we can see our encrypted RSA private key that we've just generated. And we can also print out the public key too. By exporting the key. And so here we can see our private RSA key and our public RSA key. And now that we've generated an RSA key, we can now use some built-in Pycryptodome functions. So for example, we can call key.canEncrypt, and canEncrypt checks the capability for encrypting data for the key. We can also print out key.canSign, and canSign checks whether we can sign messages with this key. We can also print out key.hasPrivate, which will return true if the private key is present in the object. So we can also print this out for the public key as well. We can execute this. And here we can see that we can encrypt with our key. We can sign with our key. The private key is present in the private key object. However, the private key isn't present in the public key object. And we can also now use the keys to perform encryption. However, we can only encrypt messages which are slightly shorter than the RSA modulus. But for this lesson, that's fine because our encryption message is also small. However, we again need to make use of padding. But this time, we will use optimal asymmetric encryption padding, or OAEP, which is a padding scheme often used together with RSA encryption. So let's import that. And now we can again create our cipher. We can encrypt our message. We can execute this. And here we can see our encrypted message, which we've encrypted using our public key. So in order to decrypt it, we now need to use our private key. We can execute this. And we can see our familiar encrypt me plain text. And we can also see what happens if we try to encrypt a larger message. So we might change to encrypt to be 1000 A's. And here we can see the error plain text is too long. And when running the above examples, your output will most likely be very different because the ciphers generate different random keys and key pairs with each execution. In fact, even if you encrypt the exact same message several times with the same public key, you will still get different output. This is because, by design, the OAEP padding scheme will include some randomness as part of the padding step. And rather than just encrypting and decrypting messages with our key, we can also use the key to create and verify digital signatures. Digital signatures are based on a public key cryptography concept. Whoever signs a message needs to have the private key, and whoever wants to verify the signature has to have the public key. And since we have these components, we can create and verify simple digital signatures by performing a modular exponentiation by encrypting and decrypting a message hash. So let's start by importing from crypto.hash SHA-512. And now we can calculate the SHA-512 hash of the plaintext message. And now that we have the hash, we can calculate the integer represented by this given array of bytes. So we'll call this hashed. Specify the byte order. And now we can print this hash out. And now that we have the pieces, we can also calculate our signature by raising the hash to the power d modulo n, using Python's built-in power function and the d and n values which we created when we set up our key. So let's create our signature. We can now print this out, signature. And here we can see our signature value. And now that we have our signature, we can also verify it by raising the signature to the power e modulo n using the key material from our public key. And once we have done this, we can compare the newly computed hash with the hash we created from the originally signed message. And if these hashes are equal, then we know that we have a valid signature. Let's create our signature hash. And we can see that these values are the same. However, you don't actually have to create your own signature method. And in fact, rolling your own crypto is almost always a bad idea. A common signature standard when using RSA signatures is public key cryptography standards number 1, and we can also use a number of Pycryptodome built-in functions to implement signature verification using this PKCS standard 2, which you can find in the official Pycryptodome documentation. Whenever using crypto with Python, make use of standard algorithms and implementations which are fit for purpose. So for example, don't do what we did in this lesson. Use tooling, mechanisms, and approaches which are tested and known to be secure, good cryptography practices. But that's it for now, and in the next lesson, we are going to cover ArgPass.